All right, so let's go to the second part to finish off section 4.2 on linearization and the error estimate. All right, so I have said this before, but if you are given the function f is equal to, y is equal to fx, then dy, which is defined as the derivative times dx. Okay. Now, instead of particular point A, I'm just using x as a generic independent variable. Dy written as the derivative f prime times dx is called the differential. And differential of f. Okay, and this notation basically is based on the fact that f prime is dy dx, but we can write this as a differential. And many times we have equations that involve these differentials. And of course, those are called differential equations. We have an entire course on differential equations. And so you will probably be taking that because the reason you are learning calculus is because you want to find maximum, minimum, you know, shapes of graphs, but ultimately most people would require some sort of a differential equation to solve their engineering or science or math problems. All right, so for instance, if you're asked to find the differential for this, okay, how do you find that? Find the differential of this function? Well, all you have to do is basically to differentiate this. It's 2 times e to the 2x, and just put dx at the end. That's it. Okay, so there's absolutely nothing difficult about this. If you are asked to find the differential, then differentiate the function and put dx at the end of it. All right, so the last thing I should mention in this section is this error computation or error calculation. All right, so we're going to use inequalities and absolute values. All right, so this is actually quite a practical thing, and this will estimate sort of like measuring errors and things like that. All right, so here's a problem. Okay, this is a problem from the OpenStax textbook. Example 4.10 is what it is referred to in the book. Okay, let's say you have this cube. Okay, the cube means that the height and the length and the width are all the same. Each side is 5 centimeters. Okay, so it's 5 centimeters by 5 centimeters by 5 centimeters. Well, in the real world, you don't have a single cube which measures exactly 5.00000 centimeters without any errors. Okay, so let's say you think it's 5 centimeters, but you can call this a manufacturing tolerance or manufacturing error or even measuring error. We think it's 5 centimeters, but actually this could be off by 0.1 centimeter or 1 millimeter. Okay, so each side, let's call this x. So we know that x is 5, give or take 0.1 centimeters. Right. So in other words, we think x is going to be between 4.9 and 5.1 centimeters. Okay. So find the volume. The question is, how much can the volume be off by if the error on x is 0.1 centimeters, right? So v is x cubed. No problem here, right? So here's the differential, and this is maybe your first application or the second one after linearization. The second application of differentials. dv can be written as what? 3x squared times dx, right? Okay, right. So the absolute value, see, the thing is, this can be written as absolute value of 0.1, right? That's plus or minus 1. Actually, I should say, I'm not saying this right. I'm saying plus or minus 0.1. If you take the absolute value, it is 0.1. Give or take or plus or minus can be easily written by or using the absolute value. So what we are saying is dv, depending on, if this is plus or minus, the error for x could be plus or minus. And so the absolute value of dv can be written as, of course, the absolute value of 3x dx, but here x is positive. Okay, x is definitely a positive number. 3 is also positive, so you can take that away, and so you can write it this way. Okay, now x is given us 3. Sorry, 5. So this is 5 square dx, and so that's 75 times the absolute value of dx. Now we know this is saying that the difference, the real difference between 5 and the real side length, that's the error on the side length, error on x, is less than 0.1. Right, so we know this is going to be less than 71 times 0.1. Well, that's 7.5. Okay, so what are we saying here? V, the error on V, is at most 7.5 what? Okay, this is volume. It's 3-dimensional, so this is cubic centimeters. So that's an interesting thing, right? Because you're saying, well, look, this is a fairly accurate reading. Each side can be as big as 5.1 centimeters, as small as 4.9. That's not a big deal. But if you are using that measurement to calculate the volume of this entire cube, the error could be as big as 7.5 cubic centimeters. All right, and that's called the error estimate. That's not exactly the right answer, but using the approximation by differentials, this is what you get. So the error on V is approximately as much as 7.5 cubic centimeters. All right, and so that's it. How do we get this? Well, again, you start with an equation that you know, take the differential, and you are trying to find the error on the differential using what's given. Okay, so this part was given, and this part was given as at most 0.1, right? So this was 0.1, but because this number turns out to be pretty large, the error estimate is also a little large. So this is called an approximate error estimate. I guess I should say error estimate. Okay. Sometimes it's called an absolute error estimate. So if y is fx, dy, the absolute value of dy is called an absolute error, and it is estimated by using the differential estimate, absolute error estimate. Okay, but here's something else also, right? In this case, v was, what's v? X cubed, right? dv is 3x squared dx. So if you think of dv over v, the absolute value of this, what are we talking about? It's the error divided by the volume, okay? And this will have a meaning, just a minute, okay? So if you calculate this, this will be 3x squared dx over x cubed. These are all positive values, except we don't know about dx. So this is 3 over x, and then dx, right? Okay. Now, if x is 5, this is 3 over 5 dx. And this thing is, remember, 0.1. In fact, at this point, we can use the inequality because we are given that this is not just 0.1. It's less than or equal to 0.1. And so this is, well, this is 0.06. It's 0.06. Okay, because this part is 0.6, right? It's 0.06, which is 6%. Now, what do we calculate? Right. This is the error divided by the volume. So this is a percentage of error based on the volume. All right, so this is called so dv or dy over y. This is called relative. And the word relative simply means percentage at this point. It's a percentage error estimate. Okay, so what this is saying is, if this is off by, in this case, 0.1, right, centimeters, then it's off by, the volume can be off by 6%. And that is what this is saying. Okay, actually, at this point, you could have also said 3 times dx over x, right? So this is actually the relative error of the what we calculated. Okay, relative error of the this, and that was let's say, what is that? 5 millimeter point 0.1 over 5 is 1 over 50. That's 2%, right? So 2% relative error on the side length is going to create a up to 6% error on the volume, and that's because it's a three-dimensional object. Okay, well, anyway, so that's the one. I should do one more example before we finish. So let me just give you one last example of absolute and relative error estimate. Okay, we have, let's assume you have a circle. So here's a circle. Good. Let's make sure this is a real circle. 0.88 times 0.88 inches. Okay, so this is a circle. Radius is 10 inches, plus or minus 0.2 inches. Okay, let's say I ask somebody to draw a circle of radius 10 inches, and the person says, well, I couldn't make it too precise, so there may be a plus or minus 0.2 inch error. Right? So this is an error estimate for R. So find the absolute and relative error of the area. All right, now the area is, of course, pi r square. Okay, so dA is 2 pi r times dr, right? This is a differential of A with respect to R. So you can say dA is 2 pi r and then dr. Now dr is, well, in this case, R is given as 10 and dr is plus or minus 2. So the absolute value is 2, right? Yeah, I guess I should say at this point, because we don't know dr. Dr is at most plus or minus 2. The absolute value is at most 0.2. So this is what you get. So this is 2 pi times 0.2. It's 20 pi times 0.2. That's 4 pi, right? And so that's approximately 12.57. Oh, that's, sorry, it's in inches, isn't it? Yeah. So what this is saying is, because we don't know how accurately the circle is drawn, we think the area of the circle is 100 pi. But with this kind of an error estimate, if the radius can be off by up to 0.2 inches, then we are saying that the area could be off by up to 12.57 square inches. All right, that's the absolute error estimate. Okay, now the relative error estimate is always dA over A. And what is dA? It's 2 pi r dr over A, which is pi r square. Now, all of these, well, first you can cancel. And so you get 2 r and then dr over r. By the way, this is actually saying that the relative difference, the relative error in the area is going to be 2 times r. It's proportional to 2 times r, and then the relative error of the one-dimensional one-dimensional measurement of the radius. Right? Now, for this problem, it says r is 10, so this is 20, and then dr, r is given as 10. Sorry, that's not quite right. There's no r in here, it's 2, right? What this is saying then is that the relative difference of the area is actually twice as much as the relative percentage error on the measurement r, right? And so this is 2 over 10, and so this will be 0.2 dr. And of course, that's less than or equal to 0.2 times what was dr? Dr was given as 0.2, right? Plus or minus 0.2. So this is 0.04, and that is 4%. What this is saying then, by the way, if r is 10 and the error, dr is 0.2, that is actually what, 2%, right? 20% of this will be 2 inches, and 2% will be 0.2 inches. So if the radius measurement is off by 2%, it could cause the relative measurement error of 4% in terms of the area, and that's because the area is a two-dimensional object relative to the r. Okay, so that's the this is the relative error estimate. Okay, so this is what you can use the differentials for.